Hello everyone. I'm Takehiro Hasegawa, the master student from the University of Tokyo. Today, I talk about our research about Takorobo. Firstly, it is said that the soft robot control is difficult, and one of the reasons is that the soft robots have nearly infinity degrees of freedom. So the model-based control needs very high computational power. And also, when you try to increase the computational power, for example, sensory mechanics or computer, it loses the merit of soft robots. The softness of the body will be lost. But there's one way to use the soft body of the soft robots as a merit as the computational resource. And this physical reservoir computing called PRC can be used for the soft robot control. I think you already know about this, but this is the basis of our research. So I shortly explain about the reservoir computing. In reservoir computing, the recurrent neural network called reservoir. The reservoir computing is a machine learning method that use recurrent neural network called reservoir. And the weight in the reservoir is fixed, and you can obtain the target function by adjusting only the weights of readout layer. Then, when you input the output of reservoir computing to the reservoir again, the loop is closed and this becomes a single system. Then, in physical reservoir computing, dynamical physical systems are used as the reservoir of RC. Then, values observed from the physical reservoir, for example, in soft robots, that is basically the sensor values, are used as the readout values of reservoir computing. And robot control using such closed-loop physical reservoir computing are expected to be useful for the adjustive behaviors of the soft robots. And previous research has focused on the PRC control of soft robots, which have only single soft components like octopus and spine of the quadrupedal robot, and so on. So in our research, our research objective is to control the whole body dynamics, whole body behavior of the robot, which have multiple soft components. Then this is the image of Takorobo we made for this research. Yeah, it's so simple robot, but how large is it? Here, yeah, this is the real Takorobo we use in the research. Yeah, this robot has 4 silicon sensorized arms, and these are driven by the servo motor at the base. Then we use the flexible sensor in this in each arm that is because the ordinary robot sensor as bench sensor used in the famous octopus arms experiment can only bend in one axis, but we want to move arms in every direction. So we use the capacity growth as a sensor by measuring the capacity of the sensors. So it can move or reflection. Yeah, then, and by the way, the reservoir computing is basically supervised learning. So we need to decide the target behavior. Then, such target behavior should be effective itself. And also, every behavior has the degree of degree of fitness to physical reservoir computing, because physical reservoir computing is depending on its physical reservoirs embodiment. So we decide to search the locomotion that is fast and suitable for physical reservoir computing. To search the suitable gates, we limit the robot motion in this way. Yeah, each motor of Takorobo was driven by the four kind of phase. So each motor was moving in sine waves. And also, when so the gates which match when they are rotated each other were eliminated to make easy to experiment. So resulting in the gate pattern was decreased in 20 patterns. Yeah, this is the video of the measuring locomotion speed of each gate. Yeah, so many things can be said from this experiment, but it's not core of our research. So please, if you are interested in this result, please read our paper. But shortly saying, it can be said that the efficient locomotion was made by the dynamics and also asymmetry of the body robot body. As you can see in this video, the 0012 is an asymmetry gate, but this is the one of the fastest gate pattern. Yeah. Before I talk about how to evaluate the suitability for PLC, in this slide I talk about the PLC model concretely. Firstly, the robot was driven by the target motor commands, YT, as shown in red arrows. And so in training phase, we recorded the target motor commands and the sensor outputs that is used as the result of physical reservoir. And from the data, we calculated the weight matrix W and bias vector B for the physical reservoir computing. And in closed loop PLC control, the estimated motor commands from the calculated W and B was also input to the robot. And the robot is driven by estimated motor commands in closed loop control. Then we evaluate the fitness to the PLC of each gate by calculating the coefficient of determination. That is how accurately the motor command was estimated in training data from sensor data. Yeah, next graph shows the time series of sensor outputs in training phase. And from this data, by physical reservoir computing, in light, the yellow line in light figure shows the estimated motor commands, calculated from distance value. You can see estimated motor command fit to the blue line that shows the target motor commands. Then, after these experiments, the gate patterns, suitable for PLC locomotion. That means the gates which is fast and accurately estimated. Its motor command was accurately estimated. Then we selected for closed loop locomotion 0011, 0012, 0101, and 0111 gates were selected. Finally, this is the video of closed loop control experiments. Light graph shows the time series of sensor data and motor angles. Top 4 graph shows the sensor data during closed loop control experiment. Then below, the under 4 graph shows the estimated motor commands from sensor data. In this experiment, at first, robot was driven by preset motor commands, target motor commands. Then after that, the robot control is switched to the closed loop control. You can see the graph change at the intermediate time. And locomotion was generated by this video. Additionally, we tried the closed loop control in water also. This is the video of 0012 gates. In the air, the 0011 is good for PLC closed loop control. So the suitable gates is different depending on its surrounding environment. You may think, this green graph shows the motor command is separated, but the robot can continue to move. Finally, I conclude our research. Firstly, we made Takorobo to experiment physical reservoir computing using the robot's whole body dynamics. And as a result of experiments, the robot was able to continue locomotion when directly controlled by closed loop PLC. There are other experiments like position estimation was done in our research. But that is, if you are interested in, please read the paper. Also, this QR code, from this QR code, you can watch again the video materials I used in this presentation. Thank you for listening.